All right, my friends, let's get started. I hope that you really did give each of these some thought. These are all very AP style type questions. So for problem 1, it says evaluate the sum as n goes from 3 to infinity of 5 to the n minus 2 divided by 2 to the n. Whenever you see everything in your definition of terms here, whenever you see everything with a constant base and then, some variable exponent, you should probably think, at least consider that this might be geometric. And you can also fall back on if in doubt, expand it out. So I'm just going to show what that looks like. So if n equals 3, then I'd end up with 5 to the 1 divided by 2 cubed. And then if n equals 4, I'd end up with 5 squared divided by 2 to the 4th. Remember, it takes 3 terms to establish a true pattern. So let's go ahead and plug 5 in. So I'd end up with 5 to the 3rd power divided by 2 to the 5th power. So now if I look at the terms, I would just ask myself, do they keep just multiplying by the same constant value to jump from one term to the next? And the answer is yes, which means this is geometric for sure. And not only that, it's an infinite geometric. And what is the common ratio? What are they multiplying by every time? Well, they're multiplying by 5 halves. So they keep multiplying by 2.5. So I hope it makes sense that the terms themselves are going to diverge to infinity. So the sum itself would also, of course, diverge to infinity. And so if the direction said evaluate, and so I guess I would say it equals infinity. There you go. Somebody asked, does it converge or diverge? I would say it diverges, and I could even tell them that it diverges to infinity. There you go. Okay. For problem 2 here, express the repeating decimal as a ratio of 2 integers. And there's more than one way to do this problem. I know that. But I am going to ask you, even if you had a different way to do this, that you kind of follow the logic here. Because in the next problem that's going to be like this, it won't have numbers in it at all. It'll have functions of x. Okay, so let's make sure you can do this in a way that will be sustainable if the math gets a little more interesting. Okay, so the first thing that I would kind of recommend that you do here is notice that this decimal has a repeating part, and then it has a part that doesn't fit the pattern. So what I would recommend you do is take anything that isn't kind of part of the repeating piece and just kind of split it off. So and then from there, what we're going to do is turn the repeating part of the decimal into an infinite geometric series. And so it would look like this. So 1 plus, and really we're just focusing on this repeating part right here. So I'm going to write it like this, 0.09 plus 0.0009 plus 0.000009, etc. Hopefully that makes sense, that would equal this repeating part. And then let's look at this and hope that it's geometric, because it certainly isn't telescoping. And there's only 2 types of infinite series that we can evaluate exactly. They are geometric and telescoping. So let's hope this sucker is geometric. So what would you multiply 0.09 by to get 0.0009? I hope it makes sense. You're multiplying by 1/100th. And then the same thing when you jump from 0.0009 to 0.000009, you're multiplying by 1/100th again. And so this part in the parentheses, my friends, is geometric. It's an infinite geometric, and its common ratio is 1/100th, and so it will converge. It will add up to something finite. So as far as this 1 goes, you just kind of keep bringing it down. We'll add it in later. And so now let's use the sum formula for an infinite geometric series right here. So it would equal your first term divided by 1 minus your common ratio. There we go. And so let's see, up to you how you want to figure that out. You're in Calc BC. I'm sure you've got ways, right? Anyway, I like turning things into fractions for these personally. Flip and multiply, the 100s cancel, and you'd be left with 9/99, which would reduce to be, what would that be, 1/11th? 1 and 1/11th. There we go. Okay. And if you have a calculator handy, it wouldn't hurt to just take a second and, do 1 plus 1 divided by 11. And then, you know, watch how fun the decimals look. There you go. Okay. All right, my friends. That's problem 2. So be prepared for that kind of move where you write a repeating piece as a geometric series and then use the sum formula for it, as long as your common ratio is between -1 and 1. Okay, let's look at problem 3. It says determine the convergence or divergence of the series. The sum as n goes from 6 to infinity of 1 over the quantity n minus 5. For that one, there are different ways to do it. You could do, you know, some comparison work. You could use limit comparison test for sure. Integral test, I'm sure you could do that. But I want to show you another way to go about it. You could actually fall back on if in doubt, expand it out. So notice that if n is 6, you'd end up with 1 over 1, or 1. If n is 7, you'd end up with 1 over 2. If n is 8, you'd end up with 1 over 3, and so on. And so this sum right here, my friends, is actually a p-series. It's also known as the harmonic series since your p-value is 1. And so you could actually notice, let's see, another way you could like redefine it. So this is the same. I wouldn't use n again. You'd use a different variable, maybe k. This is the same as the sum as k goes from 1 to infinity of 1 over k. This is called using a dummy variable, where k would equal n minus 5, essentially. And so basically, you diff and out, expand it out, and then notice if it could have been defined simpler. And you wouldn't have to write this part, but it is kind of cool to have that experience of seeing that you could kind of redefine it in simpler terms. And so the point is that this is a divergent harmonic series, or I'll just say p-series. And I'm saying that because your p-value would have been 1. There we go. Okay. All right. So problem 3 is dedicated to many ways to do some of these problems, and sometimes look for the simplest way. Okay. Problem 4, true or false? If false, give a counterexample. So the statement says, if your terms go to 0, that would mean the sum of those terms definitely converges. And so I'm hoping that you said false to this. This is a common trap that calc students can fall into, is thinking this. But a counterexample, seems like that should be 2 words or hyphenated or something. But anyway, a counterexample is actually right here with problem 3. Problem 3, if you look over here, the value of your terms are going to 0, but they just don't go to 0 fast enough to add up to something finite. They actually blow up to infinity. And so the harmonic series is always a good counterexample. And so the sum as n goes from 1 to infinity of 1 over n, it diverges. In particular, it diverges to infinity, but that is even though the terms themselves do go to 0. So there you go. All right, my friends, I hope you enjoyed a little mixed review. I'll try to throw this in here and there just to make sure that you're as prepared for your AP exam as possible. Take care, everybody.